Thank you very much. And I will, I usually start with thanking my co-authors, and since there is a review paper, there are so many of them from various places, Ruti, Dani, Zviel from Tel Aviv, Marina from the Bogomolo from the Technion, Jonathan from Ben Gurion University, Philip Stark and Will Fittian from Berkeley, Chiara Sabati, and Asaf Weinstein from Stanford, Yotam from Carnegie Mellon, and Christine Peterson from AMC Texas. And as you can see, many of them, quite a few of them are sitting here in this room. So I'm very privileged in that. Now, why is selective inference important? It is really strongly related to the replicability of problems in science that actually have been realized for, I think, about 20 years, but didn't get that much attention. And it's the work of Ioannidis with this title of why most research findings are false, and the abstract says that he has a proof for that, really caught the attention of the public and the regular newspaper. And so you can see New Yorker, The Truth Wears Off, and Trouble in the Lab, and so on and so forth from this 2010 on. And it didn't take long that the fire caught also our most established journals, scientific journals, and Nature has about reproducibility, a whole volume, and a lot of other discussions. In particular, one can see that the attention attracted the psychologists who were blamed often for problems, and they had a project of 100 studies in which they were asked other authors to replicate the results, and estimating reproducibility of psychological science that ended up last year. And from here, you could see that if this was the results of the first study, and this was the results of the replication, and this was the effect size and effect size, all the red ones didn't replicate in the sense of 2/3. The p-value was not less than 0.01, but you can also see that the effect size in the replication study are much below, or tend to be below the line of equal effect size in both studies. So, before I continue, and it will be important for the last part of my talk, I want to make some clarification of replication, reproducibility. Emmanuel was also asked about that. And essentially, to reproduce a study from the original data through analysis to get exactly the same result as appear in the report or in the paper, being able just to follow up on that. But the replicability is replicability of results. That is, we replicate the entire study from enlisting subject through collecting data, analyzing the results in a similar but not necessarily the same way, and still get, not exactly, but approximately the same results. And the confusion is, in some sense, it's funny. So there is, in a paper that appeared about reproducibility is not replicability, the statement is reproducibility is the ability to replicate the results. So, but for me, it is important to realize that there are two aspects. And that one is that, we can assure reproducibility of the paper. We acquire and we can see if it is reproducible, but it is impossible to check the replicability of a single study. You can only enhance it. So that's the purpose of doing selective inference. Now, enhancing replicability, so it is agreed upon by almost all that well and transparently designed experiment is a requirement, and that reproducible data analysis and computation is also necessary, and this is agreed by our major scientific institution. Also, it is agreed by all that statistics has a major role in this game. But what role? What problem should it address? It wasn't clear to many, and so science, for instance, 2 years ago established a committee that is supposed to help the reviewers, the regular reviewers, in reviewing papers regarding the statistical aspects and thereby learning what are the problems that need attention. But this void was filled very quickly by arguing that the fault is that of the p-values. And so a psychological science, in a paper, 6 to 8 researchers shifting from reliance on, anyone knows what is that? Null hypothesis statistical testing. We have published a tutorial by Cumming, a leader in new statistics movement. Anyone knows what is that? Okay, so there are 20-something recommendation, and 9 is do not trust any p-value. Whenever possible, avoid using statistical significance of p-value. Simply omit any mention of null hypothesis. But routinely report 95% confidence interval. So this was the first step, but another psychological journal went ahead and just banned them. And this is a less important journal still. From now on, this journal is banning the use of null hypothesis statistical testing. Prior to publication, authors will have to remove all investigates, p-value, t-value, f-value, et cetera, et cetera. We're out of business. So given all of these attacks on the p-value, the American Statistical Association decided to take action. And there was a year-long process, at the end of which the SA boards published a resolution. And the resolution is that appears in American Statistician, and it opens with the statement that the p-value can be helpful, and then it comes a list of do not, is not, should not. It may lead to distortion of science if you use a hard threshold, and so on and so on. All warnings in terms of the p-value. Now, at the end, it concludes in view of the prevalent misuses and misconceptions and so on of the p-value, then some statisticians prefer to supplement or even replace the p-values with other approaches. So it is the p-value's fault in this committee's opinion. I was part of it, but I couldn't stop it. And obviously the responses on the web, we finally get rid of the p-value tyranny. So what were the other approaches? Well, there were confidence interval, prediction intervals, estimation, likelihood ratio, Bayesian methods, and so on and so forth. All have the same kind of problems. Let's take in particular the confidence interval, okay? And we have a field where in some journals, confidence interval completely forbidden. In epidemiological study is a p-value free zone for quite a few years. And so a study by Giovanezzi and al. Looked for a relationship between more than 100 types of food intakes and the risk of prostate cancer. And the abstract reports only 3, 95% confidence interval, no p-values. Okay, so apparently only those 3 for which the relative risk in terms of odds ratio do not cover 1. Okay, those are 3 reported. And the conclusion that you should eat ketchup pizza and avoid prostate cancer not surprisingly found its way to the broadcasting and the TV and to the media. It's a wonderful study. So if you do use something that controls for selection in this particular study, like using the false coverage rate, controlling confidence interval that addresses selection by constructing, instead of 1 minus alpha confidence interval, the number selected over the number in the pool. So it will be 3 over something like 120 confidence interval, and all 3 cover 0. But it wouldn't have made it to the TV Now, this is not unusual. It's not a problem of epidemiology. If we looked at, with the help of a class of my students, we looked at the analysis of the 100 papers in the Psychology Reproducibility Project. And the number of inference per study ranged between 400 and 700 in a single paper. The average was 72. Only 11, as the American president now say, very, very partially addressed the selection. So what are, in my view, the two main statistical obstacles to the problem of replicability? They are addressing selective inference and addressing the relevant variability. And I'll, of course, talk only the first one of the two. So selective inference is simply inference following the fact that you have learned something about the data. That something has turned out to be of interest after reviewing the data. And then you have to worry about what happened to your usual coverage, error, estimation, and so on once you have selected. So how is selection manifested? I would divide it to two. There are in-study selection, which are evident in the published work. When you have 700 or even 72 and things, and you can find them from reading the paper, this is in-study selection. And it's selection in the abstract, in a table, in a figure, highlighting the things that pass a threshold, or selection by modeling, whichever model selection method you use. All of these are it's clear from the paper what is being done. And then there is out-of-study selection, and this is regarding the file drawer problem, as it is called, publication bias, and the garden of forking paths, and all p-hacking, all those names that come to mind, and they are, in the sense, evil, because Taylor said in his interactive data analysis, you need to confess about them. So this is the kind of things that I'm talking about. And in my review here, since I was, I guess I pressed myself into putting into the position of presenting challenges, so I will review the area only as needed to present the challenges. So it is biased, it is not complete. I will have some well-formulated, meaning math challenges, and some less formulated conceptual challenges. And if I mention a challenge and somebody did hear something, raise your hand and write it down, and I'll collect it later on, because it will be clear that some of the things have been addressed by people sitting in the crowd. So just a framework, I observe Y1 to Ym statistics. Yi has some distribution. The expectation of Y is mu I. If I'm testing the null hypothesis, mu I equals theta I, and I have M of these, but also I can go to 1 to infinity, or I even can belong to a region in two-dimensional, or one-dimensional, two-dimensional, and if it's the brain, three-dimensional situation in practice. And the regular marginal test is the probability of rejecting H not I when it is in fact true, and we want to assure it is less than alpha. And the regular marginal confidence interval is the probability that mu I, what is that? Forget about it. It doesn't include in the confidence interval simply, and the data-dependent selection rule, which is important. This is, I'm looking at the data and deciding to select some subset of the parameters and test them or make confidence interval for them or even estimate them. And there are 4 approaches to addressing selective inference. And they are related to the error rate that you choose to control. The first one is simultaneous over all possible selection rules. So simultaneous over the selected, save our souls, on the average over the selected, which is the FDR, FCR, and conditional over the selected. Okay, and I will go along my review along these 4 that were, even from the name, you can tell that the that this one implies this one, that this one implies this one. That's maybe less clear, but also that this one implies that one. Okay. So simultaneous overall selection rules, that is the family-wise error rate, family-wise error rate. And for testing, I will put Ri if the ith hypothesis is rejected. So R is the sum of Ri, the number rejected. I'll put Vi if a hypothesis is rejected in error. And so V is the sum of the Vi rejected in error. And I want to ensure that the probability that V is bigger than 1 is less or equal to alpha. So the probability that I'll make even one error will be less or equal to alpha. Same thing about confidence interval. The probability that what happens when you move to this system, the probability that there is an I such that mu I doesn't belong to the confidence interval is less or equal to alpha. And what happens if you ask for that? I mean, if you ask for that, that is the probability, you don't allow even one I, the confidence interval will not cover it. Now, this holds for any other subset. So you can, from the selected with protection of family-wise error, you can then sub-select anything that you want, and the same property will remain. So that's why we call it selection over all possible selection rules. And the methods, well, you're well familiar with Bonferroni, alpha over M, to create, say, confidence interval using the square rectangle. And you can use CDAC if they are independent and work at this level, a little bit less than Bonferroni level. And a recent contribution by Royan for a 40-year-old standing theorem is the fact that if you're working with normal mu sigma, you can still work at this one and be conservative. And this is a recent result from 3 years ago. And the reason is the acceptance region is convex and symmetric. And so the probability under independence is the smallest possible for normal distribution. Post-selection inference created by the group by Burke et al., the group in Penn, is actually another example of that. They take the regression problem with X, the design matrix, and look at all possible models, linear models that can be generated from this. And still, you want to control the probability of making even one error from this large family. So even if you take your own one or you do forward selection, you have the right coverage. Okay, so I'm to my first challenge. Okay, so we have Y, which is normal 0 sigma. And we look at the maximum two-sided test. And sigma ij is any correlation matrix with rho ij. And instead, you take the average correlation matrix, that is 1 on the diagonal and rho average in every other place. Okay? Then you use the average correlation and be conservative. And so what you want is the probability for under sigma of t being bigger than t to be less or equal to the probability under the average correlation matrix. And we have a proof, there is a proof for which checked and it's okay for rho ij bigger than 0 for m equal 3. For m equal bigger than 3, there is another proof that was given by Abba Krieger, and I'm putting a question mark because we haven't checked it all the way through, and there is another 20-page proof that turned out to be false. So I'm saying that hesitantly, but I think we have a hold on that. Well, the challenge is it true for any rho ij as long as the average is positive? How is it about Rij being estimated from data? And maybe it's better to estimate and take the average because of the law of large numbers, and work with that rather than with the original RAJ, especially if you have few observations and the matrix is large. And what about the practical case where we often use T instead of normal? Do we still have the same kind of result? Well, the problem is, as strange as it looks, currently, calculation of the exact probability, software that is available can do it only up to 50 or 60, that's all. I mean, it turns out to be an enormous, for general sigma to be an enormous problem. So this can be a very useful one, and it's better than the Ryan because rho bar can be close to 1, and then you can get a lot. I mean, remember that if the correlation is 1, you don't need any penalty at all for using that. Well, let's see an example of what the family-wise error rate control does. So this is a study of a drug and natalizumab study. It was examined by Ghosh et al. In New England Journal of Medicine, treatment of Crohn's disease. They were comparing 3 regimens with placebo, 4 measures of success at 5 time points, total 51 endpoints. 1 primary endpoint, and this was just treatment by 2 infusions of 6 milligrams. I mean, just one of them was selected as the primary endpoint. The other 50 were described as secondary endpoint. And the results for the primary endpoint were not significant, but 27 secondary endpoints were significant at less than 0.05, and so they were considered a discovery, and the study reported a success. Obviously, it wouldn't have been reported as success if you took, not obviously, you have to look at the numbers, but none of them pass the Bonferroni and any of this. So it looks maybe that SOP, simultaneous over everything, is a bit too strong. The next one is simultaneous over the selected. Okay, what is simultaneous over the selected? It is the selection rule we have is determined before observing the data. For instance, the largest, we'll take the largest, we'll take the 5 largest. Okay, we'll take the forward selection with some stopping criteria at 0.05. And then what we want is, it looked well on my computer. Okay. That's why I like better to project from my own. But for test, it means that you sum, not over everything, you count the errors only in the selected one. So you take the number selected, okay, and you count the number of errors, but only in the selected ones. And you want this to be not more than alpha. So before I collected all errors, now I collect the errors only over the selected, okay? And I wanted the number of errors, the probability that the number of errors will be bigger than 1 to be less or equal to alpha. And for confidence interval, it simply means that I don't want to allow that there will be even 1 confidence interval not covering, but only among those that were selected. So if I'm looking at the model selection, look at the end of the coefficient, all I care about is the coefficient that I've selected, and not about the thing in general. And so obviously from this definition, it is a weaker condition than simultaneous overall selection probability. And let me give one example of the thing, how it may work. It is really work in progress with Philip Stark and Jotam Hertlinger. So the example is choosing the maximum of 2. It comes out, you do in an epidemiological study, adjusting for age and gender is almost mandatory, but then you can have many more possible confounders. So you would look at, do you look at the result of the coefficient of a risk factor by itself or adjusted for age and gender, the best 2 of them. So this is kind of a typical example where you are just emphasizing the better of the 2. So the question is, can you design a confidence interval for the largest of 2? Well, we can design and use Bonferroni or the CDAC one, but can we do better than that? And the interesting result that we have is, and surprising, is that you can use here, I mean, obviously you will have the estimator, the largest of the two, plus or minus its standard error, times z, but it is enough to use z1 minus alpha over 2. You don't need to give any penalty for that. That is, the confidence interval for the maximum 2 is like the confidence interval for one parameter. How? Looks strange, but the point is we're making only confidence interval for one of them, and it holds for correlated bivariate normals as well. And the idea is you build a strange confidence region. That is, you build a region that is that if the mu is here and the mu1 is bigger than mu2, you take and x is also in this region, you take plus or minus c. And if you are in this region, you take plus or minus c on the other coordinate. And this goes to infinity. We're looking at the maximum one. Okay, it's a non-equivariant confidence interval, unusual one. But if you invert it, you get exactly the estimator plus or minus c. And so if you get the estimator plus or minus c, I have the simple proof is if you look, the z is two-sided, and z belongs to minus c. It is simply f of c squared minus f of minus c squared. Using the things that I still remember, you get this one. And because this is symmetric, this is 1, you get fc minus fc. So the probability of being there is exactly alpha if you choose z 1 minus alpha over 2. And it works for correlated Gaussian because this thing, if you switch it, if you turn it up here, and if you switch it this way, this completes this to a long strip that in order to have probability alpha, you need plus or minus 2. Okay, what happens if we look at the maximum of m bigger than 2? There is and you compare it, this is the CDAC, and this is the new one. Then the amount, the adjustment factor between the two is, of course, there is no need for the regular one, and you see the advantage going on. Essentially, it looks like a one-sided modulo interval. What happens with, if you don't want the maximum of the absolute value, it becomes even more complicated. The confidence region is something like that, the same idea, but you have to worry about all of this. But the interesting result is that if you use it, and if the interval is bigger than the regular one, than the unadjusted one to 1 point by 12%, as the mu gets away from origin, you don't need any penalty, and you end up with the one-sided, with the one-dimensional confidence interval. Okay, no inflection, neither. So, what are challenges? There is a conjecture, which are always true, have it, and that says that the least favorable. It says that we are out of battery. I think that's a very nice start. So, we are. That about the least favorable situation. But let's see, what are the challenges in that? First of all, is the confidence interval remain conservative under dependency? And second, how far can we go with this approach? I mean, this is really a beginning. We don't know how far. Can it be used for simultaneous over selected for forward selection in the lasso situation? Some work in this direction was done by Gorman and Solari. I think the next talk by Roquan, if I'm not mistaken, will have something to say about this direction. Yes? And what about point estimation? We know nothing about that at all. The importance is that there is a move today towards more and more registering of the first part of your study as the confirmatory study, with registering it at the Open Science Consortium and so on. And so you have to specify, but still we cannot specify that we'll do something and not worry at all, completely specified. So this might allow you, both to specify a method and to get protection against the effect of the selection and allow you to select, because I believe in selection. You just have to do controlled selection. Okay, on the average over the selected. On the average of the selected, essentially the false discovery rate is controlling on the average over the selected. So I will state it differently. SY selects the rejected hypothesis. The number of rejected hypotheses is the size of the selection, of the selected set. So V is the number in SY of type 1 error, and so the false discovery proportion, which is V over R, can be seen as the sum over the selected of the error divided by the number selected, and 0 otherwise. So FDR is essentially on the average type 1 error control over the selected. Okay? And for confidence interval, you can define the false coverage statement rate exactly in the same way. Just put in the bar VI equal 1 for a non-covering interval, and you count the number of non-covering intervals divided by the number of intervals that you make, and controlling that is the control of the false coverage rate. A reminder of the BH needed? I don't know. Oh, I hope so. Yeah, okay. So yeah, after I talked at Stanford, and at the end of the talk, somebody came to me and asked, "But what is FDR?" So I simply you take the p-value, you sort them, you take the largest case so that the p over all j such that pj are less or equal to q times 0 over m, and you reject all those hypotheses with p-values smaller than the pk. And you reject none if none exist. And if you look at the adjusted pH, that means take pj multiplied by m divided by j and take the minimum of that, and that's essentially the q value also. Okay, why do I want to mention that? We know that this procedure controls the FDR at level q for independent test statistics, for positive regression dependent on a subset, which means that if you take one variable from a subset and you condition on it, and you move the value on which you condition, any monotone set will have increasing probability. And this implies MTP2 as connection to the talk we heard from Lovician. And also for one-sided test, and the Gaussian distribution where all of the entries are positive. That's enough to have PRDS. So two-sided, studentized, independent, in spite of the fact that they have positive correlation, are also protected under that, even though they are not PRDS. But could we use something like Royan results to get the result that we wish, that even under two-sided situation, we have the right coverage? Well, it doesn't work. And this is because the acceptance regions for the, say, in the case of two tests is a region of this form. This is convex and symmetric, and this is convex and symmetric. But unfortunately, when you bite out the corners, you're out of convexity, and so you cannot use. However, and there are counterexamples. We can create counterexamples where this will knock. However, this is a very particular one. You see Qj over m. We take little pieces. The bites are small. We are not too aggressive. So there is hope that this will be the case. And indeed, the big challenge that the BH is conservative for two-sided tests for Gaussian distribution test statistics under any correlation structure is strongly supported by simulation. For instance, Weiner showed that the worst case is ρij equal 1, and Cohen showed that if ρij equal 1, I mean for every one for which the null hypothesis is true, then the FDR is less or equal to alpha over m times over m, which is the usual constant, times 1 plus sigma 1 over j, starting only from m naught plus 1 to m. And this thing is less or equal to m naught over m. So we are still conservative. And I know that Emmanuel has conducted extensive research with students trying to break down this, and it didn't work. And we did that, and Roquin did that, and one of the results of this conference is we decided to sit down tonight and maybe be able to do something seriously in this direction.
The problem, I think, I mean, if I may interject with it, is the problem when you have correlations is that FDR, the Benjamini-Huntworth procedure, will do rejections in blocks under correlations. And so when you look at your realized FDP, it's not concentrated around the mean anymore. And I think people, as you know, people resisted the FDR initially because they said, what does it mean to control a thing in expectation? But then I think they all realize that there's some sort of ergodicity when you have independent test statistics, which means that you're never far from the mean. And so people were extremely reassured with this. And I think that's why it became a very, but under correlation, that's not the case anymore. And so you could end up in a situation where, yes, FDR is controlled, you're right, but then when you look at the outcome or you study, you have no idea where you are. And so I'm not sure that
I agree.
You see what I'm saying? Is that we have to be, controlling FDR may not be enough under correlation, that's all I'm saying.
That person, I mean, I really hope this does turn out. Of course, it's important to realize that in the Natalizumab study that I showed before, if you ignore selection at all, 27 are selected. If you use FWR, none are selected. If you use FDR, 18 are selected. So the conclusion in the Real Journal of Medicine could be justified. The use of weights, you can introduce weights to the definition of the false discovery rate and false discovery proportion by not counting merely the errors, but adding weights to making a false error, adding weights to making rejections, and then define everything in the same way. And there is this set of weights was discussed by us. Genovese and Wasserman has a new one, and recently Ramdas et al. Have all, including everything, studied at all kinds of weights and so on. The point I'm trying to make in this challenge is the fact that the practice is extremely important. For instance, if you take the current US practice for primary and secondary endpoints, that if you have a primary endpoint, you can reject it, then you go to the secondary endpoints, you don't have to control at the 0.05, and you can even publish it on the label of the drug. If it doesn't pass, then nothing from the secondary is allowed to get. And strangely enough, this is described by using exactly the weighted false discovery proportion and the procedure that controls it, but gives 0 weight for the secondary endpoints and weight 1 for the single primary endpoint. And this means that you can put everything that passes 0.1 on the label. Something like I think it's the wonder drug, and that exists there on the label, and you can support it by things that pass the 0.05, even if you had 27 of them or even more. So the point here, the challenge is really the use of weights, and people don't use enough weights, but use weights in particular setting and adopt them for the particular setting. It's a conceptual challenge. I think it should be answered. The hierarchical framework, I will mention it shortly, even shorter than I planned, for a good reason. But I do mention that the idea is that you will have, the idea is you arrange the hypothesis that you want to test in an hierarchical structure, one leading to the others, subfamilies according to, from a single, and then you test the subfamily of rejected parents hypothesis by some procedure, and then you go in only if you rejected something. So you first test this one, and you see which one you have rejected and which one you have not. You continue with the rejected to their children. You test each one of those. You test here this one. You look at the rejected, and then you continue only with the rejected, and you stop with that. And so, and the idea is that there is meaningful concept like control over a layer, control over the entire tree, or control over endpoints of the tree. So this is an endpoint, this is not anymore. and this is an endpoint, and this is an endpoint, controlling of the endpoint of a tree. And there are meaningful concepts, beautiful results, but they require independence between the parent and the child. And this is something that doesn't happen often. It's the result, as I mentioned, of Dani. So we encounter more of this in recent research, inference on the selected families. This is the results from association between volume changes in the voxels with genotype, Alzheimer's disease initiative. And the paper of Stein has only this graph at the end of this picture. At the end of it, these are SNPs, one SNP, another 5 top SNPs. And for each top SNP of the almost 500,000 SNPs that were researched, only 5 were selected. And in each of these, the voxels in the brain were searched, 32,000, and only the selected ones are displayed. So the point is that essentially you see that the researchers looked at SNPs as a family, and then inside the SNP, you can see that there are another family of testing that is being done. So it's a family of families, and this is a way to approach this almost 13 billion hypothesis, association hypothesis that are being tested. So utilizing the hierarchical structure, and I will, the idea here is again on the average over the selected. So if Hij is the hypothesis in the family I, and then in each one of them, for each one of them you have test statistics or p-values, and you have S of p is the selection procedure of families, and then you have the number of families selected. It's a random number of families selected. And then if you take any error control, which is the form expectation of some error measures, which is the false discovery, family-wise error rate, and other generalization, and you try to control on the average over the selected families, meaning that you take the random error rates, say the false discovery proportion, and you take the average over the selected. The problem is you need a special tools for that. The BH over all hypothesis may be too liberal for the family level, and so on. I will skip the next slide simply because the 5th challenge is to develop methods that address such complex structure, okay, to address such complex structure of families. And you will hear, you will hear both in Heller's talks and Sabati's talk, you will hear more on this direction. But I want to change that in spite of this talk, there will be much more that has to be done. So addressing dependency, addressing topological features. First you look at cluster or at level, and then you go inside and look for peaks and things of that sort. I don't know if you will address some of this. No, but Yakir had some work on that. Looking at graphs, looking at adaptive methods. I mean, the whole point is that if you have this huge complex situation, you have to try to sort them according to the needs of science and be able to do that. I'll finish in this one with a complex example of a 6-layered graph of association of gut microbiome in colon cancer, where in essence, it turns out that the researchers are interested not even in the particular species. If no species was identified, even knowing something in the family is important. So you have this. Okay. Okay. I will, how much time I'll have? The 5 minutes of the switch? Okay. So, oh, if 1 minute, I will just say the following. Okay. Let me mention the challenges one by one and look at and then leave this as riddles to the crowd, okay? So the challenge number 7 is for you. It is avoiding the use of p-values for testing, and is the use of negative control in research, or the use of knockoff for testing, which is a synthetic way of generating matched negative controls. And the challenge is, can it be taken further to confidence interval and to estimation? In testimation, where we know that the FDR has been giving excellent asymptotic results under independence, the challenge is what happens when we consider average squared error over the selected, not over the entire vector, but only over the coefficients that are non-zero after thresholding. That's a completely new measure to work with. And the challenge 9 is that this testimator, that you use FDR testing and then you estimate only those that are significant, this testimator is a penalized model selection for orthogonal X. How about its performance for non-orthogonal X? And there are hits in both in Gavrilov works and both in Bogdan and Manuel's work on the slope, and probably maybe in Abramovich talk about that. And then finally, when we look at conditional over the selected, which is the last one, and there I look at the probability of non-coverage under I, and you look at the select of the largest one, bigger than 2 or something like that, or if the p-value is less than 0.05. Well, if that's the case, you can create conditional confidence interval, and this was done initially by Hedges, then by Zong and Fetis, and more recently by us. And then you can see the conditional maximum likelihood estimator behaves like that, and the confidence interval is bigger. And I'll go all the way to where I opened the talk and look again at the graph and realize that the 100 papers that were selected for replication were all significant result. So the p-value was less than 0.05 in all of them. And if you use conditional confidence interval, being p less than 0.05, the confidence interval have to be much larger. And what you see here is the conditional intervals, even for things like that, which go well beyond 0. So getting the next value of things which are not at 0 shouldn't be surprising. So I have only 12, so. So the challenge number 11, okay, I will just say that I feel more comfortable with conditional analysis when replication can be done while controlling the conditioning event, like the example that I showed now. Should it bother me? Are there places where we should be more comfortable about conditional analysis and not other ways? I do sympathize a lot with the work that was done by that Jonathan Taylor presented, where I wish I would be able to have a system that produces reproducible computing, and the computer will record exactly what you do. And then at the end of that, you will get a conditional assessment of what you did. So no confession is needed. Do reproducible research, everything is recorded, you can wander as much as you want and still get a conditional assessment. So I will summarize and say that I hope I convince you that selective inference is an important area. I hope I convince you that it's an area where a lot is being done, but much more has to be done in that sense. And the has to be done is both technical, mathematical in that sense, and both conceptual in that sense. And I showed 11 challenges, and 12th one is left for you. Thank you.